Hello everybody. This is the beginning of our 32nd video lecture. And I want to start today by passing out the last homework assignment. So there's good news and there's bad news. The good news is it's the last one. The bad news is there is one. Has to do with limits of functions, cluster points,
How are you?
I'm okay. Continuity is also on this. Let's see, today is Wednesday. Let us have it due. Never, yes, I heard that. How about a week, a little bit longer than a week? So,
Next Friday.
let's see, our test is on, yeah, that's exactly right. Our test is on the 29th, Wednesday. That's right, 2 weeks from today. So why don't we make it on Friday? Maybe you can help me, Melissa. So not this Friday. It's
April 24th.
okay.
2016.
It's due
Solid one.
April 24th. That date is very familiar. 2015. That's a Friday. It's not this Friday, but it's the fall Friday. Okay. Okay. All right. So that's where we are. We're talking about continuity of functions at 2 months. That's what we are. I need a little refresher. What was the last thing that we did? I know we did some examples of continuity. And we showed a fact about the cluster points and f being continuous if and only if, thank you very much, if and only if the limit as x goes to c of f of x equals to f of c, for c being a cluster. Okay, that's where we had left off. And we've done some examples for continuity. And what I want to pick up with now is a big fact. And what we had done, we spent a lot of time in this class about sequences. Okay? And then we went on to limits of functions, and we related limits of functions to sequences. So that's how we learned about limits of functions. But when this last fact, if you will, kind of related that we had, if you have a cluster point, if you see what's a cluster point, it related continuity to limits of functions. So that's kind of good. So we're learning about new things by relating it to things that we have studied. Does that make sense? Well, the next biggest fact relates continuity to sequences of sequences, I should say, real numbers. And here it is. So that's what we're starting with today. This big fact. The big fact is called the sequential criterion for continuity we will abbreviate that SCFC. And here's what it says. It says a function. So here's what it says. A function f going from A to R, so its domain is that, and it yields out real numbers, is continuous at C, element of A, okay, if and only if for every sequence x of n that's a subset of A that converges to C has the property, or then f of that sequence converges to F of C. Converges F of C. That's the statement. Let me get out of the way. We'll look at the proof of that. Okay, so proof will assume that we're talking about a function that goes from A to R and C in all my value. It's an if and only if statement, so we're going to have two directions. Let me get just everybody's answer. First direction, this way, and what we do is we assume, suppose, F is continuous at C. Okay. What is it we want to show? We want to show that anytime you give me a sequence in A that converges to C, that F of that sequence will converge to F of C. That's what we want to show. Let me say how we do that. We can't really do it, show it for every individual sequence in A that converges to C. So we take a generic sequence in C. I'm sorry, a generic sequence in A. So let X of n be a sequence in A such that the limit as n goes to infinity of X of n equals to C. We want to show that the limit as n goes to infinity of f of X of n equals to f of C. That's what our goal is for this part. Okay. Well, how am I going to show that the limit as n goes to 50 of X of n equals to f of C? Well, I could use the definition. It's for a sequence of numbers. Sometimes I say sequence of functions by mistake. Sequence of numbers. How do I show a sequence of numbers converges to f of C? Well, we have a set format for this every time. We say let epsilon greater than 0. That's right. Let epsilon be greater than 0 be given. And to show that a sequence converges, we need a K. That's right. That's right, John. That's right, Dalvin. That's right, everybody else. There's a natural number such that for all n bigger than or equal to k, absolute value of f of X of n minus f of C will be less than epsilon. So I'm looking for this K. It's so nice to have a clean board. April 24th, that's my anniversary. My wife asked me to go see I can't believe I'm going to say this. My wife asked me, I'm so uncultured, okay? My wife asked me to go see, I think it's concert. Look, I'm going to say this phrase, Mozart's Requiem. Did I say something that anybody says, oh, I know these words should go together? I said, Mo who? Mo who? Mozart's. Okay. There was this guy who studied Mozart's music, and he went to where he was buried to try to get inspiration. And after being there for several days in a row, he started hearing music. And he said, I must be imagining this. I've been here too long. And it sounded a little different. It sounded kind of funny. And so he went to get a professor at the local college to come listen to the graveside. Sure enough, the professor came and said, yes, this is Mozart's Fifth Symphony, but it's being played backwards. In some sense, Mozart's is decomposing. Thank you for laughing. That's very polite. All right, that's enough. All right, so I'm looking for this K. That's what we're looking for. All right, well, how am I going to get to this K? Well, I know X sub n converges to C, so that generates a K. Does that make sense to everybody? That's probably where it's going to come from. I'm also assuming that F is continuous. And we want to get the output values F of X sub n very close to F of C. So maybe I can do that through continuity. So here's what I'm going to do. I'm going to say this. Since F of X is continuous at C, then we've been given this epsilon. So there exists a delta greater than 0, such that for all x element of the domain A, with x minus c being less than delta, then that's the value of f of x minus f of c will be less than epsilon. Hey, as long as the input values are close enough, as long as the input values are close enough to C, the output values will be very close to f of C. Okay. How do I know that I can make, well, what are the output values that I want to be close to C are f of x sub n's. So if I could get the x sub n's to be really close to C, the output values will be really close to f of C. Well, how can I make the input values of x sub n be really close to C? Well, they're going to get really close to C because x sub n converges to C. Okay? So since the limit as n goes to infinity of x sub n equals to C, then there exists a K on the natural numbers such that for all n bigger than or equal to K, that's the value of x sub n minus C. I want it to be close enough such that the output values will be within epsilon units to C. Well, as long as that the input values to C are within delta units, so here I just say let this be less than delta. Normally we have epsilon there when we're talking about convergence for a sequence, but here I want this particular delta to be within this delta units. So, for all n greater than or equal to K, we have x sub n minus C less than delta, which implies by the continuity that f of x sub n minus f of C will be less than epsilon. So for all n bigger than or equal to this K, hey, the distance between f of x sub n and f of C is less than epsilon, so that tells me that the limit is n goes to infinity of f of x sub n equals to f of C. Equals to f of C. That's half of the proof. Now we need to go in the other direction. So what's the other direction? So we suppose that this statement is true. Suppose that for each sequence x sub n that's a subset of A with the limit as n goes to infinity of x sub n equals C, then it forces that the f of x sub n converges to f of C. Okay, that's the reversed hypothesis in this if and only if statement. And what is it that we want to show? We want to show that f is, that's right. at C. That's what we want. So I think I'd use epsilon delta here. Okay. Well, we want to show that F is continuous at C. So let's just stop there. We got this thing that we can use to work with us about the sequence to maybe get the result that we're looking for. But let's just concentrate on we want F to be continuous at C. Really, we can break this down into two cases based on C that we can use previous facts about. So C's in A, I know. But just because you're in A, you can have two options. We know you're in A, but you could either be a cluster point or a non-cluster point. Now, if C is not a cluster point of A, then what do we know about the continuity of F at C? Not a cluster point of A. Then by a previous result, we did last time,
It has to be continuous.
then F has to be continuous at C. That's right.
Hi, Brad.
Brad, here's homework. 5, new one. It's due on not this Friday, but a week from Friday, so we got about 9 days. By a previous fact, as John said, F is continuous at C. So that's like case 1. If, for the only other possible case, C is a cluster point of A, then we can show continuity as long as the limit as x goes to C of f of x equals to, not C. Limit as x goes to C of f of x equals to f of C. Okay. We can show continuity by showing the limit as x goes to C of f of x equals to f of C. Okay. So that's now my new goal for this part. If I can show the limit as x goes to C of f of x equals to f of C, that implies that with C being a cluster point, that f of x is continuous at C. Okay, well how can I show the limit of a function is equal to a number? Well, one way I can do that is through the sequential criteria for function limits. So how would I do that? I would let, what was the sequential criteria for function limits? It was where f of x goes to C of f of x equals to L, this is my L, if and only if, or is equivalent to, that every sequence that's in A, the domain of the function, that converges to C, whose none of its terms were C, has the property that f of that function converges to L. Okay? That's what the sequential criteria for function limits are. So here I'm going to let x of n be a subset of A, it's a sequence in A, endowed with the limit as n goes to infinity of x of n equaling C and x of n being different than C for all n element natural numbers. Okay? Okay. So, by assumption of this part of the theorem, look, we're assuming that anytime you give me a sequence in A that converges to C, f of that sequence converges to, we're assuming, f of C. So, I hate to run out of room here, but what I'm going to say next is, Thus, by the sequential criteria for function limits, we get that the limit is x goes to c of f of x equals f of c. So we have that the limit as x goes to c of f of x equals f of c. And so since c was a cluster point, what we have is that f is continuous at c. And that's in all possible cases we get this, that f is continuous at c. So that ends the proof.
Let me stop for a second, give everybody a second to
Look at what was done and see if anybody has any questions. Mary, here's our next homework assignment to do. Not this Friday, but the following. So about 9 days away. Has to do with limits and continuity. Anybody want to ask anything?
I think I wrote something down.
Okay.
In the forward direction, we said we want to show that the limit as n goes to infinity of f of x of n equals to c or
F of c.
F of c, yeah.
Should be f of c. Thank you. Anybody else with a question or comment? Okay. Well, the next thing is I would just like to write up the consequence of this last theorem, and that's the discontinuity theorem. Well, I don't know if I said this. So, as a definition, let me back up. If A is a subset of R, F goes from A to R, and C is an element of A. If F is not continuous at C, then we say, here's a big word, as you've heard before, F is, I'm talking about from calculus days. Yeah, discontinuous at C. It's discontinuous at C. Okay, so here's the discontinuity criterion. Says this, it says if or let A be a subset of R, let F go from A to R, and let C be an element of A. Then F is discontinuous at C if and only if there exists a sequence x of n it's in A, with the limit as n going to infinity of x sub n equals to c, but f of x sub n does not converge. To f of c. Let's look at an example of this in just a second. Go back and see this. We'll look at an example we looked at before. So let's let f of x be defined in the following way. It's going to be defined to be minus 1 if x is less than 0, and 1 if x is greater than or equal to 0. So here's what it looks like. Then f is discontinuous at x equal to 0. Okay, pretty clear here. If you take a look at the domain A is equal to the real numbers. Okay. And what I can do is if I look at minus 1 over n is n less than 1 to infinity. Okay, what can you tell me about this sequence? Does it converge? Yes. What does it converge to? 0. It converges to 0. Okay. And what can you tell me about f of minus 1 over n? It's a sequence. What does it converge to? So think about it. When you let n be 1, n is 1. You guys hear me? N is 1. Minus 1 over n becomes minus 1 over 1. That's f of minus 1. What is f of minus 1? Here's minus 1. F of minus 1 is minus 1. What if n were 2? Minus 1 half would be the input value. What's f of minus 1 half? Minus 1. Matter of fact, every one of these is minus 1. What does that converge to? Converge to minus 1. But wait a minute. The divergence criterion says if you can find some sequence that converges to the c value, the x value of interest, our c value of interest here is 0. Okay. But yet f of that sequence does not converge to f of c. But then here that'd be f of 0. What's f of 0? F of 0 is 1. Is that okay? So by the divergence criterion, F is not divergence, but it's not called divergence, it's called the discontinuity. Yeah, I made a mistake. Criterion. F is discontinuous at x equals 0. So that's an example. I'd like to look at one other example before I move on. Let me let you have time to write this down, and I'll come back to this picture just for a second. When I was a student before they had universities, I was told by my teacher, when you're looking at a graph, you can tell where the function is discontinuous. The graph would be continuous except where you had to lift up your writing utensil. Were you ever told that? You know what I'm talking about? Some of you said, yes, I was told that. That's what I was told. Well, I'd like to show you an example. That's a good rule of thumb that I was told. Here's an example. We're going to let F be equal to x squared if x is a rational number. And let it be equal to 0 if x is not a rational, so an irrational.
That looks familiar.
John, did you do this for your senior research project? As part of your senior research project?
Yes, sir.
Then this is what this graph looks like. So for irrational numbers, which I never showed in this class, but it's true that they're dense, so they're everywhere in all. You're getting a bunch of zeros here. Okay, that would value 0. But when you get rational numbers, they're everywhere too along the input values. You get x squared. Okay. And it turns out it's this fact that F is discontinuous for all x, element of R, except F is continuous at 0. Now, it's impossible to draw this graph really. You know, you gotta kind of sketch like I'm doing. But, you know, you can't put your finger on an irrational number, if you will, or put your finger on a rational number. They're everywhere, they're not. It's kind of looking like this. It's kind of hard to judge what the points are every time. But I would say you'd have to lift up your writing utensil everywhere. But yet it's continuous here. Why is it continuous? It's continuous because no matter what little region about 0 you give me, 0 along the y-axis. Okay? 0 along the y-axis. Give me some little region. That's by epsilon above, epsilon below. As long as I get really close to 0, the output values for this function will be within this little band about the x-axis. Okay? That's what happens. Why? Because if you take some little really close to 0 band along the x-axis, it's going to have rational numbers and it's going to have irrationals. But the rational numbers, you're going to get out x squared. But if it's really close to 0, when you square something really close to 0, it even gets closer to 0. It's going to be down here. It's going to be in that band. It's going to be in these little regions. It's less than that. And if you give me an irrational number, the output value is 0. Is that okay? So that's what's happening. So it is continuous there, but it's not continuous anywhere else. That's what happens. Well, this is kind of a weird function, in that we have discontinuity everywhere except at 0. So we can have discontinuity at a single point. We've been talking about continuity just at a single point. But we can extend that definition, that notion of continuity, to more than just a point, but to like a set, especially an interval. And so I'm going to write up this definition. We okay? Anybody with questions? Dalvin, we okay? Mary, we okay? So here's a definition. It says, let A be a subset of R, and let F go from A to R, if B is a subset of A, we say F is continuous on B if F is continuous for every C in B. So we're extending the notion of continuity at a point to continuity at a set in a natural way. You're continuous on the set if you're continuous at every point in the set. Here's a fact. If f of x is equal to mx plus b, with m being different than 0, then f is continuous at C, where C is an element of the real numbers. I'm not saying which real numbers, it doesn't matter. This function, so, I don't even want to take this part away. Let's even take this away. And f is continuous for, I'm saying linear functions are continuous on the whole real numbers. For every real number, a linear function is continuous. I took away the m being different from 0. Mx plus b, that's a line, isn't it? That's a linear function. That's what a linear function looks like. M and b are real numbers. Let's prove that. Okay, let's prove this. Let f of x be equal to mx plus b, and c be an element of R. We want to show f is continuous at C. I'm going to use the definition. What's the definition start with here, Chuck? That we use for a proof here, for continuity.
F's longer than 0 begin.
That's right. What do we need, Chuck?
Delta.
That's right. Such that for all x in R, that's the domain, with x minus c being less than delta, because we're talking about continuity, I didn't have that 0 there, delta. Then absolute value of f of x, Mary, minus f of c will be less than epsilon. Okay, that's what we want to show us. Okay, so I want this, f of x minus f of c. So let me write that down. What is f of x? Well, it's mx plus b minus, what's f of c? It'd be mc plus b. We want that to be less than epsilon. What do you mean? Mx plus b, that's definitely f of x. What's f of c? Well, you just replace the x by c. So we want mx minus mc to be less than epsilon. Because the b minus the b would cancel each other.
We're gonna need cases, aren't we?
We are. John, why do you think we're going to need cases?
Because m could be 0 or not 0, and if it were 0, then you could do epsilon over absolute value of m.
That's correct. That's exactly right. That's exactly right. So we want m, absolute value of m times the product of x minus c to be less than epsilon. And this is beautiful in that I all of a sudden see the absolute value of x minus c, which is what I get to control involved. Okay. So this means we want absolute value of m times the absolute value of x minus c to be less than epsilon. And so, John, you're correct. You thought very well about this. The natural thing to do to get absolute value of x minus c by itself is divide by the absolute value of m. But the problem is that absolute value of m might be 0. So that's why we have to break it into cases. So, case 1, if the absolute value of m equals to 0, then we have f of x minus f of c, which equals to the absolute value of m times the absolute value of x minus c. Well, that would just be equal to 0, which is definitely less than epsilon. So, for delta, any delta will work. For delta equal to 1, the absolute value of f of x minus f of c will be less than epsilon. You know, that's precisely because if m, the absolute value of m were 0, that would mean m would be 0. That would mean f of x, which equals mx plus b, would be 0x plus b, which would just be b. And we already showed that a constant function was continuous, and it didn't matter what delta was. And that's the same scenario we just got. Case 2, if the absolute value of m, if it's different from 0, then I know that means it must have been greater than 0. That's only the case. Then we want x minus c inside absolute value to be less than epsilon over absolute value of m. So here, in case 2, it's pretty clear what I should let delta be. Because remember, delta is what I pick to control the absolute value of x minus c. What should I let? I mean, it's staring at us. I want the absolute value of x minus c to be less than something to make f of x minus f of c to be less than epsilon. What do I need the absolute value of x minus c to be less than? Chuck, you know?
The epsilon over absolute value of m.
That's right. That's right. Okay. That's what I need to show. Hey, this is it. If you let delta be this, then you work backwards and you'll get that f of x minus f of c will be less than epsilon. That's the delta you need. Is that okay with everybody? Okay. Okay, so that's where I'm going to stop. That is the proof. So in all cases, not set up for you, it's a conclusionary statement. F is continuous at C. So F is continuous on R, the whole real number, which continues for each real number. So that means it's continuous for a whole set. That's our D. Wonderful. Anybody with any questions about that? Okay. You know, we had two continuous sequences, and we added them. You know what we got? Continuous sequence. And we even knew what it would converge to. We subtracted them, we converged, and converged to the subtraction between the limits. We use that to talk about limits of functions as well, those algebraic properties of sequences, algebraic combinations of convergent sequences to get algebraic properties of limits of functions. And now we can do the same thing for, what are we talking about now? What's this last topic? Continuity. You get the same type of statement. Let's write it up. That's what we want. So here's a theorem. Mary, here's the theorem. It says let A be a subset of R. Mark Peters, here's the theorem we're looking at. Let F and G be functions on A to R, and suppose C is an element of A, and F and G are continuous. At C. Then we have the following. 1 F plus G of X is continuous at C. This says if you take two continuous functions and add them together, you know what you get? A continuous function. What else? F minus G of X is continuous at C. 3. F times G of X is continuous at C. And fourthly, if G of X is never 0 for all X element of A, then F over G of X is continuous at C. Is that okay with everybody? We'll prove that next time. Okay, that's what we'll start off with next time. Prove these operating properties. We're getting very close to the end of the material for the class. It's kind of nice that we're ending. It's also kind of nice that we've managed to get through all the material. So I need to be very honest here. Oops, I don't think I turned the camera. Being very honest here, that it's nice that we're getting through all the material, even though I missed today. That did not have a lecture. You know, I missed 2 days. I missed a day that didn't have a lecture. And we had some weather difficulties, so we still managed to push through it. We're getting close to the end. Thank you very much for your time and patience. If you have any questions, just let me know.